So, you have three new derivatives to learn today. You could even say four, depending on how you thought of the absolute value. Exponential, logarithmic, and absolute value. So, let's start with exponential. Say you had y equals 2 to the x. I know you know how to differentiate y equals e to the x. That's easy. How would you differentiate y equals 2 to the x? We have not done that before. I could think of a couple different ways. There's one common way, but rather than just tell you, I'm going to have you think it over yourself or with your math amigos. Go, figure it out on your own. Read it to it. Just think about it. How can I do that? Nobody told me.
General?
Oh, I swear it's
X.
Hello, Francisco. How are you doing? Oh, I'm a whole bunch stronger.
You already know the rhythm?
Oh, it doesn't matter. Yeah.
Prove it or show why it is. Y equals to the x. And Barb, you got an idea math amigos? Well, Bob is here, so we got an idea. Here's something you could do. My hint is that you should change it first before you try the derivative. You don't know the derivative the way it is, so change it so it's a form you do know the derivative. Hi. Thanks, sir.
Yep, not gonna do that. Oh, are you going to go to the thing? When are you gonna be back? I'll leave it like two days.
Got an idea?
So like, so you're not gonna, I don't want to.
Okay, rather than a memorized fact, I'd like you to think this way. If any time throughout math, including calculus, if you say, man, that x up there really stinks, then that's a problem. Solve that problem. How do you solve the problem of x up there? Natural log. You should natural log both sides. Okay? How does that solve your problem? It allows you to bring the x down. Now, at that point, you're constantly saying, I need to take the derivative. I need to take the derivative. Have I taken the derivative? Not yet, but can you take the derivative now? Yeah, you can. So what's the derivative of the left side? Remember, good chain rule kind of implicit differentiation. 1 over y dy dx, which is the whole goal. What's the left side? Oh, the right side, excuse me. That's x natural log of 2. Is natural log of 2 a function, and therefore I need the product rule, or natural log of 2 is a constant, and just take the derivative? Constant. So what's the derivative? Natural log of 2. So dy dx is y natural log of 2, but preferably in x terms. So dy dx at the end of the day is what? What is y equal to? 2 to the x natural log of 2. All right, so then generalizing that to any base, rather than 2, it's not going to be 2 to the x every time. It could be 3 to the x, a half to the x, whatever to the x. So generally speaking, if it's any constant to the x, then the derivative looks like it would be a to the x natural log of whatever the base was, natural log of a. Okay? Now, memory comes and goes. If you understand that concept, you could easily just redo this process within 30 seconds and you got it back. Okay? So understand where it comes from. Any questions so far? Cool. Same idea. I totally feel like you can figure out this derivative on your own without instruction. So give it some thought with your math amigos and figure out how do you take the derivative of a non-natural log. Exchanging glances.
Oh, it's in y. I mean, that's how that's square. Yeah.
Then we'll just have to do like a log.
Yeah, you just exactly. Ever.
14. Ready? Got an idea? Don't give me that. I'll just wait for you to do it for me stuff. You know what I mean.
No, you can't.
No.
I'm having ideas. Well, change it. You know how to derivative differentiate natural log, so actually I could again think of a couple different ways. What's something you could do? Okay, 2 to the y equals x, that's true. And now you kind of know how to differentiate that, so I guess you could take the derivative there, but you could then natural log both sides of that, which makes it y equals natural log of x over natural log of 2 when you bring the y down and divide over, right?
Yeah.
That's equivalent, but now is that easier to take the derivative upon? Yeah, what's the derivative? dy dx is 1 over x natural log of 2 and natural log of 2 times x. So go on those lines. Okay, so generally speaking, if you take the derivative of any log, base whatever, a, then it would be 1 over, instead of x natural log of 2, it'll be x natural log of whatever the base is a. Okay? Okay, so if we were to show both analytically and graphically why that must be negative, the first part analytically would just be to show me what's the derivative. What's the derivative of log base 1/2 of x? Using that form we just said. 1 over x natural log of 1/2. Okay, natural log of a half. Here's 1. Isn't natural log of a half about here? And so that is negative, right? Okay. Graphically, when I talk derivatives graphically, I'm looking at tangent slope. 4 log base 1/2 of x. This might take a little bit of review. That's a log graph of natural log. But how do you graph any old log, particularly if the base is less than 1? What does a graph of a log with a base less than 1 look like? Do you remember? if you have log base 2 of x, it would be something like that. But log base a half of x is more like that. Partially, I wanted to review this because I felt like we'd be rusty. If you take the graph of any log where the base is less than 1, just like exponential growth goes the opposite way. Exponential growth goes this way if the base is more than 1, and this way if the base is less than 1. Same goes with the logs. They decay differently. Now then, tell me, why is this negative? Derivative is negative because slopes at any point are negative, yeah? Okay. Enough. That's gonna, so this is how this will go. You're gonna do quite a few of these on the homework for the next 4 or 5 problem sets, and they'll get into your brain, and then they'll kind of go away, and they'll leave your brain. The good news is on the AP test, they don't show up much, maybe 1 out of 45, maybe. But we will review it in time, and so it'll be in your brain again by the time you take the test. All right? Absolute value. I'm going to go a little beyond what the book does in preparation for, you'll see. But absolute value derivatives, you can sum up basically by one word piecewise. You cannot do the derivative on an absolute value function by just saying, forget it, I hope it doesn't have any effect, I'll just pretend like the absolute value doesn't even exist. All right? You must address the issue. So say you looked at any graph f of x. If f of x's graph looked like this, something like that, then what would the absolute value outside look like? What happens to the graph when you take the absolute value? Yes?
Below the x-axis just goes.
Okay, so perfect. So 1 to 3 would look like this. So to sum it up then, because the absolute value is on y, it's changing y sometimes. For positive y's, or positive f values, what does absolute value do to positive? Nothing. No effect. Okay? Now, for that then, I'm referring to the part where there is positive y's anyway, they were totally unchanged. Nothing happened. Okay? For negative f of x's, though, obviously they get made positive. Negative f, or negative y, gets made positive, so it gets flipped up. Okay. Now, this always, students think, I don't need to talk so much about this, I get it. Let's just bear with me, okay? You'll see. One thing you need to be aware of in terms of calculus is that's going to be a problem. What do you see now at that flip point? Yeah, there's a sharp turn, okay? So on absolute value often causes no derivative at the flip point. You're going to often get a sharp turn all of a sudden with that absolute value, and the derivative won't exist there. So you'll have some critical numbers. Now that will make sense because those critical numbers are going to be absolute minimums, or absolute and relative minimums. That is going to be the lowest point of the graph. So if that's a critical number, it makes sense. So let me show you what a problem will look like. Say I gave you f of x is the absolute value of x squared minus 4, and I wanted you to find the derivative of that. You do the derivative almost completely in terms of absolute value. There's a bit of a gimmick. We'll talk about it in a week or so. But for now, we're going to do it the normal way, which is to go piecewise. First, sketch the graph. What does the graph of that look like, please? The parabola is shifted down 4, but then the bottom part gets flipped. So it would look like a W. I think you'll agree. What's the y-intercept at the vertex? 4. Yeah. All right, cool. Now then, rather than try and take the derivative on the absolute value, we rewrite the absolute value as an equivalent form. F of x, besides being absolute value, could also be written as, we'll call it a 3-piece function. Some people call it 2, but I'm going to call it 3. The left part, was that part where f was positive changed at all? No. So wouldn't you agree that's just normal x squared minus 4 for x less than or equal to 2? Okay. The part between negative 2 and 2, is that normal x squared minus 4? Or was that normal x squared minus 4 flipped up? Flipped up. Now if it's flipped up, then I take the exact opposite of every one of those values. And so in here, it's actually the opposite of x squared minus 4. So you could write negative x squared minus 4, but you could also just write the opposite of both terms, right? Yes?
Should it be, for the first part of the piece function, be x is less than or equal to negative?
Negative. Yes, thank you. Yes, you're absolutely right. Okay. Thank you. Now this is between negative 2 and 2. I remind you on the piecewise, you shouldn't include the equal to or the endpoints in both sections. So include it in one or the other. I don't care which one. If you didn't include it here, then it should be included there. And if you didn't include it there, then it should be there, vice versa. Right? So it's not wrong if you put it in the middle. All right, last but not least, the far right side. Same x squared minus 4 or opposite x squared minus 4? Same. So x squared minus 4 greater than or equal to 2. I'm including on the edges, the outside edges, but again, you can include in the middle. Now, with that done, you're home free, because if I want the derivative, all I have to do is take the derivative of each of the pieces. What's the derivative on the far left side? Slopes are 2x. Let's check to verify that makes sense. Over there, are those positive x's or negative x's? Negative. If I put negative x's into that rule, what kind of slopes will I get? Negative. And does that make sense for that graph? Yeah, it does. Okay. So that's for x less than negative 2. Now, I'm not including this because the derivative does not exist at negative 2. Do not include it. There's a sharp turn there. So the derivative on the inside is certainly negative 2x. Again, verifying that makes sense. That does make sense because for the negative x side, that would come out positive, and that looks positive. At 0, it's flat, which makes sense. And at positive x's, those are negative, and that would come out negative. So that seems to work, right? Negative 2 to x to 2, and then the final derivative then is 2x. And if you think about that, that also works. Are you with me? Okay. Try this one on your own. And then the last one's pretty hairy. How's it going? I assume by your silence you're not being rude and not answering my question, you're just working stuff. Okay. Why did you get that graph?
Just what is the rules if you go up and down?
So, good question. If it's, first of all, my thought process is, I know x cubed base graph is this, so the shape's fine, right? To answer your question, then, if it's with x, then it's changing x, and therefore it's a right-left shift. It actually goes the opposite of what you might think. Subtracting 1 is right 1, because it's not so much about what's here, but what would be here to make it 0. Wouldn't you agree that to make it 0, x would have to be positive 1? So that middle flex point that normally happens at the origin.
But then
Oh,
well, then for the top one, why did we shift on the y-axis?
because that wasn't in with the x. It was after the function. You really think of x squared as the base function, and the subtracting 4 is coming after that. So it's making a parabola completely, and then changing it, which means making y, then changing y. So it goes to inside with the x or outside after the function. Okay? Okay, so my graph was a cube shifted right. Yes, sorry.
Does this have a sharp turn?
So that's a good question. That's a really good question. That's why I put this in here. Let's see.
Yes.
So, do you agree with my piecewise, first of all? Yeah. All right. So, let's talk about this. I think you'll also agree that this is this and this. All right. So the question at hand, Hunter's question, and a darn good one, is what about the derivative? Sharp turn, don't include it, like I just did, or not a sharp turn, include it.
Sharp turn.
Not a sharp turn? Why?
Parabola.
Okay. What on a cube, what does the slope approach as you go to 0? 0. So if you were to look at the slopes here, as you draw closer and closer, the slopes are 0, yeah? Now when it gets flipped up, these are still approaching 0, and aren't these also approaching 0? And so is that a sharp turn, or from both sides, the slopes are approaching 0? And you are correct then. It does exist at 1. There is not a sharp turn there, so you should include it. Not a sharp turn because the slope was 0 at the flip point, which is actually different than this guy. This slope is definitely not approaching 0 here. Before, it was something like steep, and now it's positive steep to negative steep, just like that. Whereas now, this guy is flat to flat. It's fine. All right, so this is pretty rare case, but I want you to be aware of it. Most times the derivative will be a sharp. All right, an ugly version, and then we'll be good, is something that's a little harder graphically to figure out. Tell me, if I were to graph lightly, 1 plus 2 sine x, no absolute value, how would it look? Tell me about the graph. Shifted up 1, and the amplitude is 2, so it'll go up to 3, and without the absolute value, it would go down to -1. The period is a normal 2 pi, and so in 2 pi, it might look like that, yeah? But because of the absolute value, it's actually going to look like, let's go in red, this. Okay? Sharp turns there or smooth? Okay, there'll be non-differentiability there. So, if it's ugly / unknown graph, then you must start by finding the zeros of the inside to find where the flip happens. Okay, I need to find these points so when I write my piecewise, I know, where it gets flipped and where it doesn't. So I need to set 1 plus 2 sine of x equal to 0. Sine of x equals negative 1/2 at, please tell me your trig skills are there. Sine is negative 1/2 is the negative 1 to 2 opposite to hypotenuse. What are those angles? 7 pi over 6, thank you very much, and 11 pi over 6. All right, now because it ends at 3 pi over 2, I'm actually not going to get all the way to 11 pi over 6. It's ending here, and so the flipped up graph ends there. So in terms of piecewise, will I need 1, 2, 3, or just 2? Just 2, okay. So thankfully I was throwing you a bone there, trying to save you some time with that 0 to 3 pi over 2. It's not the full sinusoid. It's only that part. So give me f of x in a piecewise fashion, please. This piece, is y getting negated, flipped, or is it straight up normal? Straight up normal. So the first piece is just normal, 1 plus 2 sine of x. From where to where? 0 to 7 pi over 6. And shall I include that 7 pi over 6? Is it, don't include it because there's a sharp turn there, or not? Yeah, we're not on the derivative yet, so don't talk to me about sharp turns yet. I'm just talking, is that point there? And the answer is yeah, it's there, right? How about from 7 pi over 6 to the end? Same old y or opposite y? Opposite y. So negative 1 minus 2 sine of x from 7 pi over 6 to 3 pi over 2. Normally I would say 11 pi over 6, but they stopped it at 3 pi over 2, which is before I get to that 11 pi over 6. And I need to include 3 pi over 2, but 7 pi over 6 is included, for me, anyway, the first piece, right? So that's great. Now we're ready for our derivative. The first piece, what's the derivative? 2 cosine of x. And what about the domain here? Shall I now include, actually, let's start with 0. Does the derivative exist at 0? Still. Yeah, it's still there. It's smooth there, so we're cool. But what about at 7 pi over 6? No, that's a sharp turn, so do not include it now. And the other derivative. Negative 2 cosine of x from 7 pi over 6 to 3 pi over 2. And what about at 3 pi over 2? Does the derivative exist there?
Yes.
It does. Okay, so there's your answer. Okay, cool? Good. All right, I debate whether to... I think I'm going to come back to this piece. I'm going to come back to this piece a little later, okay? So don't stress. Did I get back? Did you get your homework review 3?
Yes.
All right. There are a few things I was grading at and looking at that I wanted to talk about. So just a real quick note, and then I'll get to questions on 71 if you have them. The first is some people either had big old question marks on number 9 or did it wrong. So some of you who did this right, how did you get started on that? Yeah, you separate the two. Can I do that with either numerator or denominator, or only with a numerator sum? Yeah, only with the numerator sum. So 9, if you did not know what to do, that's what you should have done. Then it's u sub of 10. Okay? This is also pretty hairy. Some people killed it, but some people did not execute it well. Do you want to talk about this? Or no? Yes, okay. So the idea is you want to get to this, which is arc sine of u. You get the 1 first. So I need to deal with that 4. I factor out a root of 4. Now that makes the 1 nice, but unfortunately it changes the 9 to gross. But it is what it is. You with me so far? 1/2, boom. Now, you make your substitution to fit the pattern. This needs to be u squared. U squared is 9/4 x squared. What does that imply about what u is then? We have x, and what's du? 3 has dx, which is great, but I need to solve for dx. What's dx then? 2/3 du. So then with all my substitutions, my half is there. In place of dx, I put 2/3 du and 1 minus u squared. Cleaned up then, that's 1/3 when the 2's cancel. And the antiderivative of 1 over root 1 minus u squared is arc sine of u. And then you sub back 1/3 arc sine of 3/2 x plus 8. Okay. This, some of you are a little too quick and careless with this. I'm pretty good at math, but I still showed work, and so I think should you at least show me some thought processes. I think you're making it a little too clean or going too fast. If w equals 2x, then this and this are affected by that substitution. First of all, dw is 2 dx, so that dx is not dw, it's 1/2 dw. So you should have a half. It's not that, not that, not that. Okay? It must have a half in it. Second, these change. If x is 2 and w is 2x, then w must be 4. Right? And so you need to slow down and think a little more instead of just randomly choosing stuff. All right? All right. This one went pretty well. Mostly, I had a mistake on my key yesterday morning, and somebody brought it to my attention, and I changed it like 5 minutes into 7th hour. So I had 19 because for whatever reason I said that 14 plus 15 is 19, which of course it is not in this one. Okay. To me, good work takes maybe 5 seconds more than crappy work. And if you just say, this is equivalent to 2 times the integral of f plus the integral of 5, that to me is better than just random 2 times 7 plus 5 garbage nonsense. Instead, it communicates your thinking. And it'll yield the right answer. This is 2 times 7. If you invert this, then you flip that. And this needs to be integrated. It's not just 5. It's 5x from 1 to 4. Okay? This was on the final exam last semester. And let me read to you the results for this question. On version A, 95% of the people missed this question. Version B, 60% of the people missed this question. Overall average, about 75% of the people missed this question. So please pay very close attention. Okay? This, first of all, part of the fault was mine. I meant for this to be calculator active, so that it's just conceptual, not integration technique. So you have this velocity function, and they give you the position of the particle at time 0, and they want the distance. How do you find distance? The integral of the, not the velocity, the absolute height or the speed. Okay. Distance is this. Would you please write yourself a note? This is distance. This is displacement. Now here's the big error. If you did initial position plus 0 to 1, 3 pi of v, what is that? It's where you started plus your displacement or change in position. Starting plus change in position gives you ending position. Okay? Starting position plus how your position changes gives you ending position. All right? So, which of these should I use to find the distance? This one. So you might say, well, then what about the initial? It is a distraction. You do not use it. It is meant to throw you off, and it worked beautifully. Okay? It does not get used. You'd use it if you want position. I had some people do this. Well, I know its distance is absolute value, so I'm going to take your position plus your distance. Now, what does that give you? Good silence. It gives you absolutely nothing. It means nothing. Okay? If I say, hey, I'm starting here on the number line at 1, and then my distance is, I went forward 3 and then backward 3. What would 1 plus 3 plus 3 mean in terms of the problem? My starting position plus I went 3 right and 3 left equals 7. What does it signify? Nothing. It means nothing. 7 means nothing. Okay? So this is not ever it. It has zero meaning. It should have been this. Do not be fooled. Do not use the distractor. It's that. Okay? This was a tough one, so I felt like I could help you a little bit here. Based on, I'm focusing on D, but I used A. Now, where's my key to this? Okay, if you did absolute max with a clue, then you should have had that G of 0 was negative pi over 4, G of 2 was pi over 4, G of 6 was negative 7 pi over 4, and G of 10 was negative 7 pi over 4 plus 8. Now, I feel like people didn't use that. They didn't know to use that. You were given this, okay, and people didn't make the transference from using this to here. It said, how many times does G equal 0? Now, if you looked here and said, well, geez, let's see, I don't know, how many times does the area accumulation 0? That's making it really hard, okay? If you're trying to think, well, when would the area accumulation from 1 up to a point be 0? That's difficult. Look here. G went from negative to positive. What must it have gone through? 0. It had to have been 0 in here. Then it went from positive to negative. What must it have been? 0 in there. Now, I know this is ugly, but it's not too hard to think a little bit. Calculator dependence be darned. What is this, roughly? Roughly. This part. Negative, go with 3, okay? So it's roughly negative 21/4, yeah? Which is about negative 5-ish. So is this positive or negative? Positive. It's positive. So from here to here, negative to positive, it definitely must have passed through 0. So use that as your guide for your solution. You would say 3 times, because G goes from negative to positive, and so passes through 0 once, IDT, and so on, okay? If you're a real thinker, yeah, go ahead.
What? Like, I don't understand how you got any of that.
Any of these?
-1 for everything except for D.
Oh, okay. So how did I get those values?
Yeah.
Okay, cool. So G of 0, first of all, are we cool on why I'm using those at all?
Yeah.
Okay. So G of 0, that's actually the source of the most errors also in the final lecture. When you're going backwards on a geometry area problem, well, you had a lot of errors here. I would strongly recommend you switch it from left to right and then you do your basics. When you do a geometric area, you first say, is the area above or below? And it's above. And what's the geometry? So that's how I got the g of 0 is negative pi over 4. Are you with me on that? Switch the limits so they go left to right. Decide is the area above or below the axis, and then geometrically find the area.
Okay, I'm still completely lost. Why can't you just, because when you're integrating, you just plug in the first number and plug in the second number? And it's like-
But you would have to integrate f, and I don't know the antiderivative of f. Are you saying, why don't I just do this? Are you with me?
Yeah.
Okay, cool. Okay. Sorry. So then after those, and I am kind of glad you asked, because this one, finding this value, if they drop you in the middle, start you in the middle somewhere, and you go backwards to get one, I'm having a lot of people making errors on getting that backwards number, so we're going to need to practice that. Okay, that's pretty much, I just wanted to touch on that a little. And I think that's pretty much it. Okay, cool. 71. Do you have questions on set? Hi, Sue. Or Ms. Brown, sorry. Okay. Questions on set 71? 1? 1, 10, and 11? I did hear 1, didn't I? Yeah. Okay.
What about 23 on the last set? Like, review 3. Did you say we're going to go over that?
Oh, did I?
Oh, yeah.
Oh, yeah. Okay, to explain it really well, I would have to take a good chunk of time, but I'm going to at least lay the groundwork here. We're going to talk about more about this. So, especially for you physics people, this is kind of a calc application problem. So, you've got this tube, yeah? And how fast fluid flows through the tube is relative to where, in respect to the center you are. It reads like the further you are out from the center, the slower fluid flows through. So if you were to talk about how fast fluid flows through, it flows through really fast in the center, but a little slower out here, and very slow out to the very edge. Okay, now viscosity and stuff, but how sticky it is along the outsides. So each second there's fluid flowing through this circle. You with me? Okay, it flows through much faster in the inside, and so more fluid's going to pass through the inside than in the outside. After 4 seconds pass, I guess you could, if we were to take a snapshot, then maybe this much, you could think of it as this much fluid had passed through. How much fluid had passed through in 4 seconds, right? Now the problem is that I know that the rate at which it flows through here is 9 minus r squared centimeters per second. That's the rate it flows through, but it would be dependent on where you are. The minute you go out here, it's different areas. And so besides how fast it goes through, I'd also have to talk about how much region is there to flow through it all. The more area there is to flow through, the more liquid's going to flow through. So besides that, you also have to take into account the rate, but the area to flow through. Now this, to me, is the more conceptual part. If I talk about the area of this or any ring, it's tempting to say something like pi r squared minus pi r squared. And that makes a lot of sense, but it's actually not how you're going to do it. Instead, look at this black ring here and think, what's another totally outside the box way of finding that area? It would be to take that ring and unwrap it. What's the length of this? The circumference, and so 2 pi r. What's the thickness? I mean, it's paper thin, super thin radius. You are, beautiful. You are. Okay. Now, this is area, so that's square centimeters. You with me so far? Now, in terms of the units, this then, rather than it being a rate at water flows through this point, altogether, this is cubic centimeters per second. Well, that's the rate that volume flows through altogether over the whole cross section. If I add all of those rates, that would be the total rate that water flows through the vessel. This is a very common blood vessel problem. If you go on to be a doctor or something like that, you might see a problem like this. The radius goes from 0 to 3. I know people say, why not 0 to 4? I thought it was 0 to 4 seconds. Now remember, this is about the radius only right now, and I'll come to the 4 seconds in a second. But right now, you're just talking about over the course of the vessel, what's the total rate that water flows through. So if you integrate that, that's the rate in cubic centimeters per second that water flows through this blood vessel. Once I have that, which you would get through integration, and I did that when I went my solution, you can integrate that and you get a number, okay, because it's a definite integral, this would be an actual number. And then what would you do with that? If that's a number or a rate in cubic centimeters per second that water flows through, to find out how much passes in 4 seconds, then you need to not integrate, just multiply by 4. The total volume then would be that rate in cubic centimeters per second, and how much happens in 4 seconds. That's how much cubic centimeters of blood flowing through the vessel or water flowing through the tube. Okay, that one was from the Harvard book, the calculus textbook they use at Harvard.
What's the answer?
162 pi. Okay. Good. That's you can guess at Harvard. 71. 1, 10, and 11. Do I have time for this? No, you're still turning it in. I'm not getting behind. We are going. I'll just check that you.
Actually, randomly just try.
Yeah, I will. If you tried it, you're good. Okay. If you left it blank, you're not good. I do not accept not trying. So I apologize. I'll tell you what I can do. I'll throw you a bone, and I will work 1, 10, 11 and post them to my website today at lunch, and you can check. Just get it to me by the end of the day, okay? 18?
Yeah.
Sorry, I didn't even. You said that, 18.
No, first thing.
18. All right. Yes, I can. Any others you need me to look at? Okay. Do you guys have answers to these?
No.
All right. Let me see if I can.
Oh, boy.
If you want. Okay, here are answers. Do you have your old packet?
No. Yes. Yes.
Okay, if over there, either today, right now, if you have it in front of you, or by Monday, Tuesday, can you get it me one? There's the old packet. There's the new packet.
Oh.
No, that's not what I meant to say. Take the new packet and give me back the old packet at some point. Yes, I want these, save a tree. I'm a tree hugger. Give me that old packet, and just throw it away.
I was just about to say.
That's the old packet there if you have it. Yeah. I'm not a staple hugger. Yeah, I don't care about staples. Any of those are staples. Have a lovely weekend, 2 days. Welcome.
Oh my gosh, it's Friday.
That should be answers from 69 to 105. Yeah, so this semester.
Yeah, those go like March.
That's right. Thank you.
I went to the doctor's office. Same, I'll go with you.
And stick in there. Have a good weekend, ladies. Stop this.